All right, so let's go ahead and go back to talking about our limits. So we should be finishing up limits this week, I believe. I still need to talk about, I believe, I think three or four more sections about limits, if I remember correctly. So let's go ahead and talk about something that's related to the concept of a limit. Today's section, we're going to go ahead and talk about continuity. That works, but none of that works. Like that. So as I said, today we're going to be talking about what do we mean by continuity. That's weird. That's not letting me do any of that. Continuity. So we're first going to talk about what does it mean to be a continuous function. So to do this, let's go ahead and just start off with an example straight out. Example one. Hopefully the board will start working properly in just a moment. Otherwise, today's going to be a lot of closing and opening. So given, okay, no erasing. Given f of x, determine the values for x, the values of x, for which f of x is not continuous. Let's do the interval 0 to 4. So I'm going to let you write this, and then I'm going to go ahead and draw the graph in just a moment. I'm going to give you a graph, and you're going to determine the x values for which my function is not continuous. So before I actually show you the graph, if you were to take a guess on what does it mean for something to be continuous, what does continuous mean? What was that? It keeps on going. What do we mean exactly by it keeps on going? It never ends. I agree that that's along the lines, but whenever we say it never ends, that's more of a thought of like going to infinity. Any other ideas? What does it mean for something to be continuous? I do agree with the idea of never ends, but we should be a little bit more exact. In particular, what do I mean by a continuous function or a graph? Yeah, that's going to be a big part of our stuff. And if I want to be really informal, I can say a function is continuous if I can trace the entire graph without ever having to pick up my pencil or pen, whatever. So let's go ahead and look at this picture. Let's see if this is working. I'm going to try one more time. Let me see if I can do a full reset for this board. So I'm going to give you a graph that does not apparently work. Give me a second. We're going to look at a graph, and then you're going to tell me where is it not continuous. Let's do a full reset. You have to excuse me for a moment. See if I can just do a hard reset like this. Right. Exit. All right. One more attempt to make this work. Sounds great. So we'll have to make do. Oh, now it decides to turn off. If the board doesn't decide to work with us, then I will call it for today. We'll see. I'm not gonna try to sit here for 30 minutes while y'all watch me try to make a TV work. I would, but there's no ports for us to even use. All right. Now, if you will pop up, please. Moment of truth. Let's see if it works or not. It works. So, unfortunately for y'all, fortunately for me, we will continue to have class. All right. So, let me draw this graph. Like so. Let's do 1, 2, 3, 4, 5. 1, 2, 3, 4. And let's draw my graph like this. Let's use red. Dot here, open circle, line, like so. Put one here, and let's do this. 1, 2, 3, 4, 5. 1, 2, 3, 4. Give or take. All right. So again, let's go ahead and figure out for what values of x is my function not continuous from 0 to 4, in between 0 and 4. So what is the first x value where this graph is not continuous if you were to take a guess based off that informal definition I gave you? When do you have to pick up your pencil if you're tracing it from left to right? For x values? So if I start from the left, I'm going to start tracing my picture, and if I pick up my pencil ever, I'm not continuous. So I'm tracing it, and then do I have to pick up my pencil to go further? For sure. So this tells me right here, I'm not continuous. What x value is that? 1. All right, I'm going to keep on going. I'm moving over. Do I have to pick up my pencil to trace the rest of the graph? Can I go through this circle? No, I can't actually touch the inside of this open circle. So I will physically pick up my finger, go to here, and then go back down. In other words, I had to pick up my pencil to continue the graph. Because again, whenever I have an open circle, I do not exist at that point. So what x value was that? 2. All right, let's keep on going. Where's the next part that I might need to pick up my pencil? 5. I agree. To get for the rest of my graph, I have to pick up my pencil. Why am I going to say I don't need to include 5? What was my instructions? I wanted the discontinuities from 0 to 4. It's 5 between 0 and 4. For sure not. So even though there is a discontinuity at 5, I'm not going to include it because I only wanted the ones between 0 to 4. So what I'm going to say here is I am not continuous when x is 1 and when x is equal to 2. Yes. We have to be careful about our instructions here. So again, I'm just asking if I ever had to pick up my pencil, we have a point of discontinuity. Because, again, informally, a continuous function, we could say it goes on forever, but more specifically, I can draw the entire graph without having to pick up my pencil. I'm gonna give y'all some time to copy anything down as needed. So I'm gonna draw some very generic graphs, and then you're gonna quickly tell me, is the graph overall continuous or not? While we're waiting on this, I want you to think about how does this even correlate to the idea of a limit? So right now we are just introducing the idea of when is it not continuous, very broadly speaking. We're going to introduce the true idea in just a moment. I would say that for this first one, I think we can all agree that these aren't connected. I had to make a jump to go from one graph to another. So because at x equal to 1, I have to make a jump, then I'm certainly not continuous. Or you can say discontinuous, same thing. Someone re-explain to me, why is this point right here? Why am I not continuous at 2? I can't go through the empty circle. Again, remember, and as a key note here, an empty circle is often going to be a big red flag saying, I am not continuous there. In other words, this open circle is a break in my function. All right, so very generically, you don't have to copy this next part because I'm just going to draw some random squiggle graphs. Would this be a continuous function? Yes, because I can just trace the entire thing. I don't got to lift my pencil at all. What if I had something like this? Is that continuous? No, most certainly not. At this point here, I would expect that I have a discontinuity. What if I have something like this? Is this function continuous? So if I want to draw it, the whole thing left to right, do I ever have to pick up my pencil? Let's try it. Let's trace it. Starting here, tracing not a problem. What do I have to do if I want to do the other line? I'm gonna hold this like a toddler with a crayon. I had to pick up my pencil to trace the entire graph. This tells me that overall, I am not continuous. In particular, I'm not continuous at this wherever this point is here. Yes, so that's a good question. What if I restricted my domain? In other words, what if I said if I was only looking from here to here? What do y'all think? Would I say that the function is continuous from here to here? Yes. So that actually brings up a good thing. Overall, you're going to hear me say the word, is the function continuous? Versus, is the function continuous on this interval? So even though we say that this function is not continuous overall, if I just say I want to focus on this one part only, then we can still say that that one portion is continuous. And we saw this here. To trace this entire portion, I didn't even have to lift my pencil ever. So this is where we're going to make the key distinction talking about, am I continuous over everything or continuous for a certain interval or a certain part of it? All right, so this is if we had a graph. What if I have something like this? This is going to be example 2. determine for what x values, the function, let's call it h of x, is equal to x squared minus x minus 2 over x minus 2 is not continuous. I'm running out of room here, so I'm just going to put CONT dot. So instead of giving you a picture, what if I just gave you a function expression, the equation? So I haven't mentioned this definition yet, but we're going to see continuous generally means that I can continue first off to plug in values, and they're all connected to each other. If I look at this function h of x, are there any values I would want to avoid? Yeah, what happens whenever I try to plug in 2? We would get 0 on the bottom. Let me write that down first. I'm going to make the claim x equal to the 2 is going to cause a problem. And we can see that. If I try to plug in 2, I get 0 on the bottom. And this will still be true. With something that, looking at this function, with something that someone may say about this function or try to do. Let's see. Let me put this in the box. Say this is going to be our final answer. Let's try to factor this. What does the top factor into, if anything? X minus 2, x plus 1, all over x minus 2. And then what would you typically do in an algebra class? You would say cancel, and then you would say this is x plus 1. So do I have a point of discontinuity, or do I not? Because it looks like it simplifies. Is x equal to 2 still a problem? So again, we simplify this into x plus 1. And I'm asking, is x equal to 2 still a problem? Or should I even think about this factoring? I want y'all to notice something. And I think I mentioned this to a couple of y'all who stayed to chat after class one time. Here's my function. Am I allowed to plug in x equal to 2 here in the original? No. Can I plug x equal to 2 into here? So I agree. But these are supposed to be equal. What's going on? We said that these are equal. We did our factoring. The algebra is all correct. How is this possible? Because I definitely can't plug in 2 into the top here. But I can plug in 2, but we did our factoring, algebra, everything made sense. They're supposed to be equal, and we know that equal means that, they're always the same. Is it not a function? It is a function for sure. Well, this goes into a very nitpicky thing. I agree. These things are equal almost everywhere except for one point. If you plug in any number besides 2, then these are the same thing, right? If I plug in, 5 into here and 5 into here, you're going to get the same value. But if I plug in positive 2, they're different from each other. So that's why I'm going to state here, if I'm asking for points of discontinuity, I do not want you to simplify. Leave it as is from the beginning. Again, these are equal except for one time. The only time they're not equal is if I plug in 2. Again, because this one, if I plug in 2 on the top, then I divide by 0. If I plug it in right here, then I get 3. So I'll restate what I just said. If I'm asking for points of discontinuity for something like this, do not factor and simplify. Just look at what you have from the beginning and work from there. Don't factor. And it's a little bit counterintuitive because from algebra, y'all are used to like, here's a problem, now factor and clean it up.
X plus 1 is not same function because that's technically where the limit that you plug into would be instead of the actual there.
Yeah, so if we were to graph these two, we know what this one looks like. What's x plus 1 look like? Or what's a graph of it?
So like just the slope and then just plus 1, so it'd be above 1.
It would look something like that.
Yeah.
Very broadly speaking. That's what this one looks like. This one right here, remember I said they're equal almost everywhere except for one time. This original graph will actually look like this.
Yeah, so x plus 1 is actually just the representative of what, if you're plugging in 2 into x plus 1, that's what the limit of that whole would be. It's not the actual representation of that.
Yeah, and that's going to give us some idea about continuity and how they relate to limits. So exactly what you're thinking of. So again, the original function looks like this. It's got a hole in it, but x plus 1 doesn't have any holes in it. This function is continuous. This one is not. So this is that very minute difference between the two. And which is why I'm saying if I'm asking for when am I not continuous, do not simplify. Just work from the beginning. All right, so I'll give you a second to copy that down. Any questions about what I've written here? My answer would just be x equal to 2. That's when I'm not continuous. Primarily for the fact that I can't plug in 2 clearly. If I try to plug in 2, I'm undefined. Or indeterminate if I want to be exact. This would apply even if I gave you something as simple as this here. Again, I'm going to keep this here. Again, we're used to algebra. We say we can clean that up. It's the same thing on the top and the bottom. We're used to writing, all right, this is equal to 1. But we run into the same problem. Can I plug 0 into here? No. Can I plug 0 into here? Technically, yes, but there's nothing to plug in. So this is our little minute difference between the two. Which is why I say keep it as its original form. All right, so now let's see how this relates to our limit and what we've been doing. So what I'm going to introduce is what I'm going to call the continuity checklist. How do I check for sure if a point is continuous or not? So continuity checklist. So first off, just a general definition. A function is continuous at x equal to c if the following holds. The limit as x approaches c of my function is equal to f of c. And someone actually brought this up, I believe, in this class, something about we can plug it in because it's continuous. It's directly related to what I have here. So my definition is for continuous. So if I ever ask, am I continuous at a point? You check this condition. And really, I can break this down into three parts. The first one is f of c defined. So what I'm writing in red is going to be the same thing as this limit is equal to f of c. They're both equivalent ways of saying it. Why do I need this condition? Well, whenever I plug in, it's undefined, then I can't do any equations with it. Same thing for the second portion, the limit of f of x, it must exist. Again, if the limit doesn't exist, then it doesn't make any sense for me to say it's equal to whatever. It's not defined, or it doesn't exist. And then usually the third condition we'll check is, are they equal? In other words, we want to make sure f of c is a number. We want to make sure the limit is a number. The third condition is making sure that they're the same number. That is, the limit is equal to f of c. So this is going to be the steps that we usually take. Our three-step plan to check if something is continuous at a point. And I'm going to give you an example in just a moment where we're going to test out this problem. Maybe two examples, depending. All right, so let's go ahead and look at our example here. Example 3. Yes, 3. The instructions are going to say, is the function continuous? Continuous at x equal to 11. So I'm telling you what x value we're looking at. Are we continuous at this point? So let's say we have g of x. And let's make it a little bit interesting looking. X squared minus 11 over x minus 11. If x is not 11, 9 otherwise. So we have this piecewise function. So if I'm plugging in a number that's not 11, I use the top. If I plug in 11, I use the bottom portion. So I want to check, am I continuous at 11? So we're going to check, go down our three conditions. What was condition number 1 again? Yeah, we want to make sure that we're defined. In this case, we're using G instead of F, but same thing. So what X value am I checking out again? 11, right? I want to see if my continuous at 11. What's G of 11? I agree. Remember, G of 11 says X is 11. If X is 11, do I use the top or the bottom? The bottom. Because up here it specifically says if X is not 11, use this. All other cases, use the bottom here. So we get 9. I'm going to take a pause there. First off, do we see why did I say that G of 11 is 9? What does this mean right here, G of 11? It just means what happens if X is 11? So again, g of 11 says what happens if x is 11. If x is 11, I can't use this. This one says use this top only if it's not 11. So my only scenario is use the bottom portion here. So is 9 a real number? For sure. It's defined. My first condition is done. Now I have to check condition number 2. What was the second condition? We want to check if the limit of, in this case, g of x exists or not. All right, so, or in this case, instead of c, we're using 11. So how do I calculate the limit? Should I use the top expression or the bottom expression?
Oh, wait, as we push 11 to the top.
Yes, remember, what does it mean for the limit? We said the limit as x approaches 11. Not necessarily we are exactly 11, we are close to 11. So if I'm close to 11, I use this expression. We're going to see something here, which is why I'm not saying right or wrong yet. What is this? X squared minus 11. I see why this is weird. Let me change this one here to be 121. That will make this a lot better. 121 over x minus 11. So again, I'm using the top here because the limit is saying I am approaching 11, not necessarily I'm equal to 11. So now the question is, how do I work from here? What should I do to solve this or evaluate? Factor? What does the top factor into? All right. Do I get cancellation for a limit? For sure. So I have the limit as x approaches 11 of, what do I have? X plus 11. What is this equal to? 22. So here I'm saying my limit exists, and in particular, it's 22. Second condition works out. It exists. It's a number. What is my last condition to be continuous? F of x has to equal f of c? No, not f of x, but the limit. Yes, the limit of f of x has to equal f of c. So the third step is usually our quickest step. G of 11 is 9. The limit, we just said, is 22. Now I'm going to ask the obvious question, is 9 equal to 22? No. Generally speaking, no. Therefore, for the third condition, again, I'm just rewriting that just for emphasis. We said 11 of g of x. We're asking, is it equal to g of 11? To answer that, we said no. Most certainly not. I failed one of my conditions. Therefore, I can say that this function is not continuous at 11. So again, because I failed the third condition, I am not continuous, specifically when x is 11. I'm going to ask a follow-up question on this. Do I always need to check all three conditions? Yeah, I'm going to make the claim that if any of the conditions fails, then we're not continuous. Why am I allowed to make that claim? If condition 1 fails, then the third one doesn't make any sense to even check there. In other words, if g of c does not exist, I'm not going to be checking that's equal to anything. It doesn't exist. There's no equals sign that we can use. Same thing over here for number 2. If the limit doesn't exist, then there's no point in even thinking about part 3, because we're going to say is equal to that limit if it doesn't exist. So in other words, if any of the condition fails, even if it's just one condition, then the whole thing tells me it's not continuous. So if condition 1 failed for some reason, I could just stop there and be done. I can say condition 1 failed, I'm not continuous. So this is us checking for continuity. So I'm going to give you some quick visual examples of what does it mean for each of these conditions to fail. But first, I'm going to let y'all go ahead and copy anything down from here. All right, so let's take a look. If you're still copying, I can go back to it after this next slide. Is defined. Not another example, just what does it mean if I failed condition 1? Just condition 1. If I failed condition 1, then I might have something like this. A graph, I'm not defined there at that point. We said from the picture, clearly this is not continuous. I cannot trace this entire graph. The limit, I'm just using g since we worked with it, exist. That would be an example where perhaps we have something like this. Can I find the limit here at all? No. Visually, this is definitely not continuous because I would have to make a jump. That's why we have this condition. Same thing for the left one. Also, this is an example of condition 3. Well, not condition 3. Let me adjust that. Condition 3, if I failed it, might look something like this. Again, this is if the limit of g of x is equal to g of c. Let's say that they're both defined. I can find the limit. I can find g of c. Then maybe I have a graph like this. Is this graph continuous? No. Does the limit exist for this one? Would it be possible to find the limit? Yes, it would be possible to find a limit. Last thing is the function defined right here? Yes, the function is defined there. So this is an example where, yes, it's defined. Yes, the limit exists, but there are two different values. So this is an example where each condition might fail, visually speaking. So all of this boils down to I have to pick up my pencil to trace the entire graph, if I were to boil it down very broadly speaking. Here we're just putting it in terms of limits. The reason that we want to introduce the limits is that you can imagine if I have a really complicated graph, I'm not going to try to draw the entire thing. I'm going to try to work with what I have. All right, so besides that, that is what I wanted to talk about for today for continuity. Again, broadly speaking, can I trace the graph without picking up my pencil? Tomorrow, what we'll probably do is we'll talk about intervals of continuity. How do I determine what those intervals are? and a little bit more practice on this here. Besides that, I will see y'all on tomorrow.